We've been looking at logarithmic functions. We've looked at the analytical format for logarithmic functions, meaning we've looked at equations for logarithmic functions and defined that they are defined as the inverses of exponential functions. Now we want to continue with another view of logarithmic functions, that is, what about their graphs? And so we're going to be looking at the graphs of logarithmic functions. First of all, we'll look at the graph of f of x equals the log base 2 of x. As you look at that, we're going to remember that if we have y equals 2 to the x, remember that's our exponential counterpart to this logarithmic function, we generated the following table of values. If I raise 2 to the negative 3, I will get 1 over 2 cubed, which is 1/8, or 0.125. Similarly, we had 2 to the negative 2 equals 0.25, and 2 to the negative 1 equals 1 over 2, or 0.5. 2 to the 0 equals 1, 2 to the 1 equals 2, 2 squared equals 4, 2 cubed equals 8, and 2 to the 4th equals 16. Now if you remember, one of our points was that in graphs of inverse functions, that points xy on function f will equal point yx on function inverse, the inverse function of f. So let's look at that with regard to this logarithmic function then. Since we have the values for y equals 2 to the x, its inverse will be our function f of x equals log base 2 of x, which we just said is going to swap the x and y values of those points. And so the log base 2 of 1.25, let's write that out, 0.125 will equal negative 3. Or the log base 2 of 1/4, 0.25 will equal negative 2. And the log base 2 of 0.5 will equal negative 1, and so on. Notice again, x and y down here now become essentially the y and the x in this case. Now, how does that work out as far as a graph is concerned? Well, we've got a geometer sketchpad graph that will help us to see the relationship between the two functions. In this case, we're going to look at some particular points. Now, I'm starting with our exponential function, f of x equals 2 to the x, because remember our logarithmic function is going to be its inverse. So, as we look at a point on f of x equals 2 to the x, that point is negative 1, 1/2. Its counterpoint will be on our logarithmic function x equals 1/2, y equals negative 1. A second set of points, remember our kind of the old standby on exponential functions, 0, 1, on logarithmic functions will become 1, 0. And as we look at 1 mapping with 2 on f of x equals 2 to the x, with its counterpart we'll have the point 2, 1. And finally, we'll look at 2 more points. Now you begin to see what that curve will look like. Here's the log base 2 of x. And as you recall, when we looked at those 3 important characteristics of inverse functions, the graphs of inverse functions are symmetric to the line y equals x. And so you see the symmetry between these sets of points as we're looking at them. So now let's go back and explore some more with graphs of logarithmic functions. Let's look at this graph, general graph of the log base b of x. You'll notice in this case that the domain of f, which means what is it that we can put in place of x up here, the domain of f is any positive real number. It's like if we took each one of these points and collapsed it to the x-axis, we would be covering the positive x-axis. Hence, the domain is 0 to positive infinity. Now, let's look at the opposite of the domain, which is the range. What if we took each of these points and collapsed it to the y-axis? We would be shading the entire y-axis, and that means that the range of our function, the y values, will go from negative infinity to positive infinity. Now, if you think about it, that's not really surprising, or should not surprise us, if you remember that when we had our inverse function of this exponential, log base b would be b to the x. The domain of that was equal to negative infinity to infinity. And the range of that inverse function was 0 to infinity. Notice that in our inverse of b to the x, the domain and ranges are switched, which again is switching x and y. That's what inverse functions do. Now, let's look at that applied to transformations of logarithmic functions. The same transformations apply that applied to other functions and the ones that we looked at with exponentials. So let's just look at some of these as examples. Let's take f of x equals the common log of x plus 1. Well, when we take the common log, or log base 10 of x plus 1, we're looking at the adding 1 inside the parentheses, which, as you recall, is a horizontal shift. And in horizontal shifts, you go the opposite direction of what you would be expecting. And so in this case, our function has gone from our regular logarithmic function and shifted back 1 unit. So looking at our point of reference for a logarithmic function, which will be the point 1, 0, now that point has become 0, 0. We've shifted to the left 1 unit. Let's look at another one. Let's take the common log of x plus 2. Now, in this case, notice we closed off the parentheses. We've taken the action on x, which is taking the log base 10 of that, and now we are adding 2 after the fact. That's adding or making a vertical shift that goes up 2 units. And so we have our original graph right here, g of x equals the common log of x, and we have raised it by 2 units. And so our point, which is 1, 0, now becomes the point 1, 2, shifting up 2. And that's true for each one of these points. On our graph, it shifted up 2 units. If we put the x in, if we put a negative in front of our expression, we're going to have f of x equals minus the log of x. In this case, you'll recall that that is a reflection through the x-axis. And so our original function, g of x equals the log of x, starts down in the 4th quadrant and rises into the 1st quadrant. We're going to have the opposite of that with this new function, f of x equals minus the log of x. It starts way up in the 1st quadrant and drops down into the 4th quadrant, a reflection through the x-axis. And finally, you recall we can have reflections through the x-axis, through the y-axis. And in this case, f of x equals the log of negative x. Now you may be thinking, wait a minute, we cannot take the log of a negative number. But remember, we don't know what number x is until we assign it a value. And so negative x may actually be a positive number, because if I let x be negative 2, negative x is minus a negative 2, which would be a positive 2. Now let's see what happens on our graph then if we do that. Well, we start with our original function, g of x equals the common log of x. If we put a negative there, now we can look at the log of minus negative 1, which will be the same thing as the log of 1 was. Well, the log of 1 is 0. Now, its counterpart over here will be negative 1, 0 in that case. And so we have a nice reflection through the y-axis, or symmetry about the y-axis. And so you've looked at several different transformations of logarithmic functions. Now would be a good time for you to go and try to practice that. When we come back, we'll be looking at more information on logarithmic functions.